And now on to the main focus of today. I'm really excited to introduce to you folks Sebastian Castro. I've known Sebastian for a few years now, so it's my absolute delight to be able to set him up before his talk. Sebastian Castro works on manipulation skill composition at the Robotics and AI Institute. He holds a bachelor's degree as well as a master's degree from Cornell University in mechanical engineering, with a concentration on dynamic systems and control applied to high-level planning and control of modular robots. His professional experience includes technical content development and marketing for robotics competitions with MathWorks and software engineering at the MIT Computer Science and Artificial Intelligence Lab, also known as CSAIL, Boston Dynamics, and PickNik. Sebastian spent a lot of time doing really fun projects within the robotics space. Sebastian also devotes personal time to robotics education through blog posts, open source software, mentorship, talks, and workshops. I'm sure some of you may have already come across some of these contributions of his. I've been on the receiving end of some of this graciousness with his time. So I'm really grateful for Sebastian's mentorship overall. So with that said, I'm super excited to introduce Sebastian's talk today, where he'll be telling us more about approachable system design for developing robotic systems. I'm really excited to hear what he has to say, and I hope you're as well. So yeah, I'll kind of wrap it up now. Please feel free to take it away, Sebastian. Thanks for being here.
All right. Thank you for the very kind introduction. My screen share should be on now. Yeah, thank you to you, Nivi, and to the whole Talking Robotics team for inviting me along to this presentation. This is really interesting because, well, you'll see that my background is a lot more on the engineering side than the research side. So when it was time for me to figure out what I should talk about, I think I basically landed on what I'm referring to as a glorified opinion piece on mostly mistakes that I've made in writing code professionally from when I started doing it to now. And hopefully some of these things translate to good lessons. But that's what leads to my talk title of Robots Are Complex, but Your Systems Don't Have to Be. And I'll tell you a little bit more about myself without repeating the introduction to help tee that up. So yeah, welcome to this talk. Thank you all for joining. So who am I? Again, this was already mentioned largely in the introduction, but I did my bachelor's and master's in mechanical engineering at Cornell with Professor Hadas Kreskazit. And the work that I did had to do with high-level control of modular robots. So this was receiving natural language specifications and being able to map these specifications to verifiable controllers that will run in the real world. And here you see a couple of screenshots of simulation versus hardware manifestations of that. After my master's, I did spend a lot of time during my career at MathWorks. So I spent quite some time doing sort of still technical, but less traditional roles like tech support, customer training, and education marketing. And I'll talk a bit more about that in a later slide. But I then sort of hit what I'm calling an early midlife crisis. I hope it's early, where I basically switched over to full-on robotic software engineering right at the start of COVID. So this was January 2020. I had 2 months where I was in an office figuring out robots, and then everything got turned upside down. But since then, I've spanned a lot of different robotic software roles, some in academia or in research-associated entities, some in the targeted more towards a product side. Now, I did enjoy the education marketing work quite a lot, so I sort of started this double life around the same time where I created my own personal website and started becoming very involved with the open source community through educational repos, examples, blog posts, as well as being involved in certain communities like the Robot Operating System or ROS community, and things like Google Summer of Code and Women Coding community most recently. So in all of this work that I've done, today I'm mostly going to talk about a few monsters that keep me awake at night professionally. We won't talk about the personal monsters that keep me awake for this talk. That's maybe outside the scope. But there's two things that I really think about a lot in my day-to-day job. The first one is this dichotomy between engineered and learned systems. And I'm sure lots of folks out here, if not everybody, is currently thinking about some version of this, right? So on one side, you have this sort of traditional manual, good old-fashioned engineering. And what I think is, at least applied to robotics, what this lets you do is to solve very narrow tasks very robustly. So what I mean is that you can put a lot of engineering into making a very robust, interpretable, with guarantees system that can solve a particular problem. But when it comes time to switch to a different type of problem or to relax some assumptions, you need to kind of stick another engineering team to recast that problem. On the other side, most recently, all these learning-based systems have shown themselves to be very generalizable, right? That the fact that essentially, if you can collect data for something, then in theory, you can also learn how to solve that task, regardless of what that task is or how complicated it might be. There's a question of scale, of course, but most recently, you've seen a lot of these scaled-up learning-based systems providing state-of-the-art performance, and that is something to take seriously. Now, there are a couple of drawbacks, not just what it takes to scale them, but the one that I think about mostly is this lack of interpretability. So this, what mostly keeps me awake is how do I know when one of these learning-based systems is working or is not working, and why? So in my experience, I sort of think there's this magical kind of middle of the road where, if you have these ML-based systems that are underpinned by a very strong engineering foundation, it actually lets you move quickly. If you want to know more about that side, so kind of digging more into this monster, I did give a talk earlier this year at the University of Washington. I think Nivi was there at that talk, so she can tell you whether to actually watch it or to avoid it or whatever. No, but in all seriousness, there is a resource there. Now, the second monster is one that I will focus on more, and this is unapproachable software. Now, this is a screenshot of something called, it's a repo called Enterprise Quality FizzBuzz. For those of you who don't know what FizzBuzz is, it's a sort of very popular introductory programming interview quiz where you basically print out the word fizz if a number is divisible by 3, you print out buzz if it's divisible by 5, and if it's divisible by both, you print out FizzBuzz. It's supposed to be a really simple problem, and this repo is actually a joke that scales this up to this super complicated, convoluted enterprise production quality version. And you've got bangers like these, like a class named FizzBuzz Output Generation Context Visitor Factory, which inherits from another Output Generation Context Visitor Factory in case you want to have different non-FizzBuzz type context. Anyway, this is absurdity, but I think there is an element of unapproachable software kind of veering to this direction. But let me get a bit more serious about this and expand on what I mean by approachable software. I wanted to use accessible, but I didn't want to conflate that with the actual legitimate field of accessibility research. So that's why I gave it a different term. But approachable software has a couple properties that I think are very good. One is that if you have a piece of robotics code that is approachable, it may not actually be the most capable, performant, optimal thing right away. However, it offers the properties that users have the sufficient on-ramp to get used to the software. So things like the code being simple to understand, having a lot of documentation and examples, and also having basically a support network that can help you with that software. So things like a responsive and helpful maintainer team. And the takeaway there is that approachable software motivates people to actually stay within that ecosystem and contribute improvements to the tools because they feel empowered to do so. So the flip side is the unapproachable software, which is, I just took the negative of all of those things. So it actually might be very good at what it does. It might be very clever, elegant, beautiful code. But if users are expected to overcome this complexity without the necessary help, whether it's because the code itself is complex or because there's no kind of social support as required, then you basically get the opposite effect, which is that it motivates people to reinvent the wheel, to write other tools or go the other way. So I think approachable software is what I pay attention to in terms of maintaining a collaborative environment versus one that is more territorial or has a lot of fragmentation. So these two monsters are alike in a couple of ways. The first one is that, again, in both cases, you could have something that works really well, and if not the best, whether it's that you have really good code or that you have a machine learning-based system that can learn to copy a set of demonstrations, but you don't exactly know how it works. But then the dark sides of this is that, one, when something goes wrong, you can't really tell why. it could either be because you have this learning-based black box that you can't really poke into, or it could be that it's just really hard for you to debug very complicated code. The same is true when something goes right, but I think people, I don't think we ask ourselves too many questions if something just kind of works. But the problem, again, in both of these is settings, you can get stuck in very unpleasant debugging holes. Actually, this talk is very well timed because we just came out of a 3.5-week debugging hole where we had at work a machine learning based system that stopped working, and it took us a while to kind of stand up all of the tooling needed to figure out what was going on. So the wound is very fresh, and we can talk more about that. But yeah, the summary here is that if you can't figure out how something works and how you can fix it, you're going to have a bad time, whether that is the technology or the approach that you choose, like learned versus not learned, or whether it's just figuring out code that one didn't write, which is always challenging, but sometimes it's more challenging than other times. Now, one thing that I want to make clear is that I'm not saying that machine learning system is necessarily unapproachable software. And I want to point people to one piece of software that exemplifies this, and this is the LaRobot framework for robot learning. I don't know how many of you have heard about this, but it is very popular. In fact, I think 2 nights ago, I updated the screenshot because they just crossed over from 19K to 20K stars on GitHub, which is pretty significant. But what are some properties about the system, despite being a machine learning-based system, that makes it approachable? Well, one is there's a lot of things like that I spoke about in the previous slides, right? There's comprehensive examples for you to get started with simulation, but also they've basically come out the gate with low-cost hardware that you can use directly to showcase their software. And of course, on the right side, you've got support for visualization, logging, and all the things that you need to gain confidence that your system works. So with a combination of these two things, plus everything else like documentation and so on, you basically end up creating this positive feedback loop where using something like LaRobot becomes the obvious choice for new contributions. So it's very easy now to say that anyone that's coming up with a new imitation learning or even some reinforcement learning frameworks for robot learning, they're jumping into getting an implementation into LaRobot, whether it's the authors themselves or doing the work directly or helping the Hugging Face team maintaining it. I think this has caused a really nice community within robot learning. So let that be very clear that the monsters are alike, but they're not exactly the same thing. But let me talk, I don't want to only talk about positive examples. I want to talk about negative ones, and there's no better way than to pick on my own work. So most of this talk is going to be tales of robotic systems, approachable or otherwise. Let me give some background. So in my last role when I was at MathWorks, I was in this education marketing role where I primarily got to spend time with the RoboCup student competition. I actually want to shout out, I see that Arno Visser is here. So I worked with him through this engagement. In fact, on the bottom right picture, there's another picture from that same event that we are photographed together. So good to see you after many years. So I worked on this for a while, and besides doing my own work, I got to observe how all of the students were competing in these leagues. And the one that stood out the most to me was this RoboCup at Home League. There's this robot that had just come out at the time called the Toyota Human Support Robot, or HSR, that you see here. And there's all these cool videos of the student teams doing things like responding to natural language and being able to integrate lots of different systems like navigation, manipulation, perception to do these complicated retrieval home service type tasks. And I thought this was so cool, primarily because of the thing at the bottom right of this video that integrates all these capabilities in robotics. I really have always liked system integration, and this just seemed really cool. So fast forwarding, I ended up landing myself a job in which I got to use the same robot. I actually saw the job posting mentioning this robot, and I said, I really want to work on this. And I was lucky to get there. So I stood up something very similar, right, where you take this natural language command and the robot has some knowledge of the world to be able to execute these long horizon tasks in the real world. So you see here the robot's opening the drawer, fetching a banana, and it's going to place it over to the desk. A lot of magic went underneath this. If you want the full details, there's another blog post here, but I'll talk about the general gist. So the way that I achieved this was by standing up a task planning architecture. And what this essentially means is that you go from an abstract representation. So you have this, language that goes through a task planner, and the task planner gives you a set of skills or a sequence of skills to achieve that task. Then, of course, you need to make those skills concretely run in the real world. And for that, I basically stood up, the fun system integrations to me layer, which is using tools like the Robot Operating System, or ROS, to synthesize things like motion planning, perception, navigation, etc., to be able to run the skills. And most importantly, when the system observes there's a mismatch between the abstract and the concrete, you have these predicates that evaluate, telling you, for example, I expected to go pick up a banana, but I didn't find a banana, so I have to now change my knowledge of the world. So, obviously a lot of work went into this, but I'm going to talk about a few stories from getting to this system actually working. The first one is this. So to implement the skills, I decided to go down the behavior trees technology. This is nothing too fancy. It's basically, taking a sequence of skills that come from a task planner and being able to put them into these little code blocks that can run in a kind of graphical structure that's easy for us to debug and understand. So what this could mean is that you have a task plan that tells you that you have to move somewhere, then pick an object, then move, then place. And the idea is that for each of these, you implement code. So for example, I decided to take on the task of implementing the pick skill. I took the robot drivers, all of the ROS communication things that I needed to do, plus the Python libraries for behavior trees, and I just smushed them all together into this tangled knot. And I got the thing working, but there were some issues. Particularly, I ended up becoming this cat, where every time that something changed in my code, a bunch more bugs popped up, and I found it really hard to manage the complexity. This particularly happened as I was, for example, in the pick skill. I started with a skill that just assumed that you always perfectly pick, but then I started adding more robustness. So, check that the gripper actually closed properly, do a couple of retries. And every time that I added more complexity into this pick behavior, I just kept breaking other stuff. And by the way, it's full coincidence that the holes in this cat GIF are actually the same as the ROS logo. It just happened to line up. So no relation there. Okay. So how did I get around this? Well, the first thing was, and I'm going to keep saying this throughout the whole talk, is that login and visualization is very important. So for the login and visualization, I'm just going to pause, actually not quite here, a little further down. So I think adding a lot of visualization was key to getting confidence that my system worked. So here's a simulation of my robot doing a pick and place task. And you see a couple of visualizations here. First of all, the simulation. Secondly, you see the object detections on the left. So I've got this, the output of my object detector plus like a filtered mask of the circular apple that I want to pick. I have the behavior tree, showing the live execution at the bottom right. And at the bottom left, I have the actual logs that are printing out stuff. So what this is showing is a behavior tree that's trying to sample a bunch of motions for picking up the apple, realizing that the apple was not accessible because there's a green can along the way. So the robot decided to, move the object out of the way, put it elsewhere on the table, and then resume with the apple picking task. So yeah, at runtime, this was great to have all this information, so I knew exactly what could have been going wrong along the pipeline. But perhaps the more important thing was testing. So one thing that happened is when I hit my peak of frustration with the software stack, I heard about this thing called unit testing, and I said, "Oh, I'll try it out. I'll make a little bit of tests for my pick behavior, let's say." And that was great. The first test I ever wrote, I actually found 3 bugs in my logic just directly from like writing one test. And at that point, I could safely say that I became test pilled, and I still am to this day. So yeah, the thing here is that it's not just being able to run the tests as you need them, but testing continuously. So every time you make a change, having the test run automatically is good. But also, and I think this is even the most important part of testing, is that when you make your code really complicated, it often is really hard to figure out how to write a test for it. So going the other way, where you have to write tests for your code, it actually makes you write your code to be much more kind of isolated. So for example, if I was testing my pick skill and I was depending on all this networking traffic and receiving images and so on, then I couldn't test it without actually spinning up the whole robot, basically. So being able to say, let me not do that. Let me have the pick skill just accept an image, and the image can come from anywhere upstream, was really beneficial. So again, this can be not fun, right? particularly if you're rewriting existing code and making it testable, it can be a lot of work. But I think the more you try this out, the more you get it right. The biggest thing to remember here is that if you can't easily test something, then maybe it's a sign that you should consider kind of splitting out the design a little bit. So I learned a lot in just this behavior tree exploration to keep my system in check, but that wasn't the end of it. So fast forward a few months, I actually had my task planning system working in both the simulation and the robot. I was really proud of this because I was able to do exactly the same thing in both these environments by just switching out a couple of lines of code. And that was great. However, whenever I had a breakage, it could often be the case that, I could be running one of these long horizon behaviors for, let's say, 3 minutes, and at the third minute, then something would go wrong and I would crash. And it was just very annoying to have to, just keep sitting there and running my code up until the point where it crashed. And unit tests didn't quite cover it all the way. So one thing that I learned, and I would recommend to everybody, is that simulation doesn't have to be a single simulation that recreates the whole fidelity of the world. You can also simplify and strip down to low fidelity simulations as you need them. So what I did is I made this 2D world, basically, that I could use it to mock my robot or my simulation and just use my whole task planning infrastructure to see if I could get this little circle robot to move around the world and do the expected order of skills that I wanted, right? So if I wanted to rearrange some objects or to grab a banana from the desk and put it on the kitchen table, I could just run this and it was, I didn't even have to run it with the GUI, right? And that made things really, really simple for testing at the task planning level. A couple of side benefits from this, by the way, were that this same UI also served as runtime visualization. And I could also use the backend to actually do all my updating of entities for the replanning part of the task planning. So it paid a lot of dividends. In fact, the latest dividend it paid is that about 4 years ago, I ended up turning this into an open source tool called PyRoboSim. You see that it looks pretty much the same, but maybe a little nicer. But I just kept pushing on this because I thought it was fun. I use this tool to teach myself actually how to use ROS2, how to set up a professional repository with continuous integration and documentation. I think I met a couple of people that I mentored through them contributing to this repository. So it was a really nice first open source experience. And most recently, in the last few years, we've actually been using this tool for workshops at conferences, or I guess tutorials at conferences, where you have people showing up to a room and opening up the simulator and trying out different kind of planning approaches. So it's really cool to see this come a long way. This is maybe an encouraging word to folks who are just getting started and want to turn some of their research or work code into something more broadly available. So yeah, lots of benefits to this simple simulation. Now I'm going to switch gears, and I'm going to talk about my second tail, I guess third tail of motion planning frameworks. So as part of some of my jobs, I've also worked on robot manipulation. So getting a robot arm to go from point A to point B without colliding and so on. And I've had to go through a lot of different frameworks. And I think one of the things that I think about a lot is this kind of dichotomy here between motion planning tools being on the simple side, but actually not being capable enough or just being toys, versus something that is professional grade and therefore has to be really complicated because you need that if you're going to solve real problems. And I want to argue that this is not actually true. This is more of a two-dimensional problem of that there can be motion planning frameworks or code in general that is highly capable, but also simple. So usually there's some kind of trade-off. This is I guess a Pareto front caricature for those who are familiar with that. But I want to outline a few of these kind of where the state of the world is right now. So on the simple side, you can think of these like industrial software tools. So I got this from a YouTube video that I found. But in the industrial robotics domain, you often are doing very, very simple motion planning tasks. Things like running linear motions or point-to-point motions that are very basic and just get the job done. Why? Because you're automating a process and you're able to control the entire environment around you. So it's okay to have something really simple where you just click and drag stuff and tell your robot to do a sequence of skills. On the other hand, you've got these more kind of research and development-oriented tools that are open source, like Drake, MoveIt, Tesseract, and so on. And these tools are very powerful. They have, motion planning and control capabilities for unstructured environments, just lots of really nice connections to the open source ecosystem, but they're all in being powerful, they're also very monolithic and complicated. And I don't know how many of you have tried these tools, but they can do lots of impressive things, but when it comes time to really dig into how these things work, it can sometimes be a little overwhelming. I myself have worked with MoveIt as part of my career, and a couple of things that we observed that led to this complexity were, one, that MoveIt actually was created with the start of ROS 1 in the sort of mid 2000s or maybe 2010. And there's a lot of assumptions about not just what code tools were back then, but also what motion planning consisted of. I think back then it was a lot more like sense, plan, act, and less online reactive motion planning like you would need in the more kind of modern machine learning era. Secondly, MoveIt was created as a ROS tool, and that meant it was very entangled with ROS, which again provided some benefits in that you had a very nice integrated system, but when it came time to unit test things or debug, this caused lots of difficulties. And the combination of these things led to challenges keeping active maintainers because they were going elsewhere, or maybe they were giving up because of the complexity. Even when I was working with MoveIt, I worked on a product named MoveIt Pro, which was also trying to kind of shift MoveIt to the more simple side of the spectrum without sacrificing too much of the capability. So there's definitely a need for being closer to the middle there. In fact, when I left PickNik, I decided I was going to go completely on the other side and kind of teach myself how tools like MoveIt work by writing my own thing in Python. So I made this educational tool called PyRoboplan that was, again, it was optimized for pedagogical situations, right? There was nothing that was too fast or optimized. It was all like Python classes that you could just see right away. And it led to some very nice educational resources you can check out. But of course, even I in the documentation, I would not recommend that anyone use this to do any serious work because it is a simple educational tool. So when it came time to think about motion planning for later jobs, we of course wanted to be somewhere in this optimal balancing of both worlds. And what we did is we took inspiration from these, kind of powerful tools, and we said, let's draw from that and take a couple steps back, create this framework for then the users, in this case, our researchers that we work with, could fill in the blanks later. But what happened is between that, the fact that we made a decision to go, primarily C++, and also that because we were using ROS, we continued having a couple design. This actually led to a lot of impediments where the tool never gained enough traction that we had users to fill in the blanks, and we ended up not really solving the immediate problems. So that was unfortunate, and we ended up kind of getting stuck in this, serves nobody space here on the bottom left of the plot. So what does it mean to actually get to the top right? There's sort of a generic recipe here for successful software, which involves having a very nice core that is very isolated, easy to use, has a lot of the support documentation examples that I talked about, without reinventing the wheel. So building on existing libraries, not adding any extra complexity, and any time that you need them to integrate with things like simulators or robots or systems like ROS, you have this optional integration layer out. And of course, this can be a set of different integration layers. The idea is that you can use the core library with different kinds of wrappers in a way that doesn't complicate the core itself, and that's still usable by anyone trying to tinker. So what that resulted in is my latest effort, I guess, that I've been collaborating with people on, which is called Roboplan. So we took this C++ library, this really nice tool called Pinocchio, that we built sort of a motion planning framework around. But two of the key things were, one, that we didn't couple this with systems like ROS. So this is going to be a separate thing outside of all of this. And secondly, that we made sure that it was possible, and in fact preferable, to also have Python bindings so that people could very easily do things like visualization, debugging, and just general hacking. So that, coupled with some examples that actually prove out that this thing works and that people can interact with, is sort of the way to go, right? You have tools that you can open up a model and you can click and drag things around. You have a lot of visual cues for what your paths look like, what your trajectories look like. Can you easily add or remove or move around obstacles in the world and see how your system changes? So people want that validation, need that validation to prove to themselves that you can do real work with these tools. So jury's still out on whether this is the right way to do things, but I feel like at this point, I've worked on quite a few motion planning frameworks, and hopefully my mistakes are useful to you as I've converged on this type of system. But let's wrap up real quick. So generally, how do we make approachable software systems? There's kind of four main takeaways I want to talk about. The first one is, I'm going to just, again, I've said these throughout the presentation, but just to recap, don't reinvent the wheel unless there's a really good need to. So in this case, if the previous wheel was square. There's this common phenomenon in software called the second system effect, where you basically decide that you look at a piece of code and you're like, oh yeah, I can fix that, I can do better. And then you end up with this super complex over-engineered system. So really ask yourself whether you actually need to rewrite something versus fixing it. And the particular things to watch out for: one, if all you're doing is you're adding new layers on top of a tool that don't actually enable anything new, then that's usually something to look out for. And this usually comes from a common pitfall of, I think it pays off a lot to take the time to learn how something works for you to decide whether it's worth investing time in fixing something versus rewriting from scratch. We often underestimate the cost of rewriting things. Secondly, you basically need to get buy-in from people before you start optimizing. So there's this quote here that talks about premature optimization being the root of all evil, from a famous computer scientist, Don Knuth. And the idea is that you always want to, or almost always want to, start with something that just does the job and motivates other people to make it do more than just do the job, but that empowers people to help. That means that you want to bias first towards solving the problems that you need to solve, and then you can clean up later after you've kind of proven out that the technology is worthwhile. And that's the mistake that we made with this work stack that we just spent too much time upfront architecting. So the takeaway here is that it doesn't really matter how elegant or clever something is if you have nobody that wants to use it. So first, prioritize getting people to acknowledge that there is a problem to solve and that everyone's going to work on something. And then I think you will be in a better place there. Sometimes you cannot avoid complexity, and I'm sorry, I'm going to put my friends in the ROS2 control community on blast here, but this is one of the first architecture diagrams you see when you go to the ROS2 control documentation. And I looked at this and I said, why do we need all these boxes and concepts just to implement a PID controller? And it wasn't until later that I realized what was going on. And the lesson here was that you have to help convince people why the complexity is warranted. You need to provide clear motivation and a lot of documentation examples and access to people asking you questions and challenging your assumptions. So there are resources out there that explain why do we need this control framework in ROS and examples that you can check this against. And it took me a while to understand that the whole point of this tool was to create something where you could reuse the same controllers on different hardware, but also use different controllers on the same hardware, or mix and match. And this mix and match point, it took me a while to understand, and it should have just been made way more obvious when you open up the repository. It should be like the first thing that pops out. So kind of, again, explaining that the complexity is for a reason and not just because. And lastly, and this is the one I probably said the most, prioritize the ability to troubleshoot. This is a video from Boston Dynamics, which is just a short clip of typical marketing material of engineers looking at a screen and seeing, yes, I can understand why the system works. But it's true, like having all these visualization tools where you can kind of scrub through the state of the robot and look at plots, or even look at things like your perception output, where is the robot going to plant its feet when it backflips? You need this stuff to verify that your stuff works. More concretely, you want to add as much login and visualization as you can because it will save your life. Unit testing, I've already advocated for it, both because it catches issues and it forces you into architecture. And really keep yourself honest. If you write something, piece of code, or you create some hardware, whatever it is, if you can't use it yourself to solve meaningful problems and debug for yourself, then what chance would other people have to do the same? So always think about these things. So in summary, these are the kind of the four main takeaways that I had. But the key one here is that you should really take some time to figure out the human part of the problem first, and it will open up the doors for you to tackle the technical ones much faster in the very near future. So thank you for listening. Robots are complex, but your systems don't have to be. Thank you.
Yay. Thanks,
We have some
Sebastian.
time for questions.
Yes. We know that you have a hard stop at 1 p.m. Eastern, so we'll make sure we're mindful of that. But folks, if you have any questions, you're very welcome to unmute yourself and ask them, or you can also drop them in the chat, and I'm happy to read it out.
I'm seeing the chat as well here.
Yeah.
I joined the Slack, but I only have the announcements channel. Is there another channel where the questions would
We'll
come?
create one for
Okay.
you. Yeah. We'll do that and share it with folks. Nitin.
Yeah. I'm gonna start the questions by asking you about a comment you made. Remember you were mentioning about Drake, Tesseract, and other similar tools, and you said that one could find that they're monoliths. I wanted to ask, has that ever been a concern to adapt it on a larger scale? Like anything that goes out of a small scale lab experiment? Like I remember, my team at work going through something similar, and I think we were trying to like Tesseract and see how that could help us or like something like that. But then we got to a point where we even spoke to the developers, but then it was hard to go ahead and make that case to someone that's not an engineer and get them
I'm
see
actually
past the
going to
concerns.
go to the plot because this is pretty important. So interestingly enough, I put Drake at the very top of both capability and complexity because I think Drake is very unique in that it's probably the best in class platform for specifically optimization-based motion planning. So if you're optimizing a trajectory, chances are that you're going to try out Drake and it's going to work really well. But yeah, there's definitely a cost to two things. One is because Drake is one of these tools that it's quite cleverly written to support different things like performance of C++, Python bindings, integration with automatic differentiation. There's all these things that make the code actually really, really hard to modify if you need to go in and make changes. So when you basically need to go off the books and not just use the tools that they've made, but to like make your own, say, optimization cost or something, you start to really eat the cost. And sometimes it can be better to say, you know what, I think I might want to spend more time bringing up my own optimization stack that I'm more in control of. And I think lots of tools go in that direction. Obviously there's Toyota Research Institute who they use Drake pretty faithfully because they have all the experts and they know how to make it work. But chances are that not everyone has access to the experts. So it's definitely a cost you have to factor in.
Thank you.
Yeah. Sanjeev, do you want to go next?
Yep. Am I audible?
Yes.
Hi, Sebastian. Nice to see you again. Thanks for the talk. I have a question like, as you mentioned, all the popular motion planning library, Drake, MoveIt, and Tesseract, and you also started this new project like RoboPlan. So just, I don't know if a personal question or not, are you planning to keep all the good things from all of these software stack and try to push the community and you also yourself to build something which can provide all of these greatest benefit from all of these motion planning software and which can also be used for the serious stuff?
Yeah, I mean, that's what I would like to do, but it's very unlikely that I or anyone will be able to do that perfectly. So I think the best thing you can do is kind of embrace the ease of integration. And this is where a tool having Python bindings is very important, in my opinion. I think it's very easy for you to let's say you take Drake and some other Python tool that exists out there. It's pretty easy for you to just pip install Drake, pip install this other tool, and you can do parts of it in Drake, get the output, and feed it into this other tool. That's usually the best we can really do as a community. The problem that arises is for something, for example, let's take MoveIt, that because it basically only works with ROS, if you have people that are not using ROS, then you really can't do that. And the flip side of that is if you are using a MoveIt or ROS-based tool, then it means that ROS starts to be a requirement throughout the rest of your stack as well, and that might not be desirable. So I think having something that you can kind of install in isolation and script with it, and then if you need to, like, just lets you make quick proof of concepts, is what I'm aiming for. And hopefully people like yourself or the community comes up with nice integration examples that, you know, connect Drake's motion planning with RoboPlan or something like that. Yeah.
I think I understood. Thanks.
Thanks, Sanjeev. Maybe I'll read out Arnaud's question before getting to you, Alessio. The question says, path planning for robot arms, for example, Move It, is quite difficult. It would help if there are good courses to teach everything that is needed in such tool. So not just the basic inverse kinematics. Do you know good examples of such courses?
I know of a great teaching professor at Northeastern out in Seattle that has been teaching a robot manipulation course. Yeah, no, but it's true. The resources are there. Actually, I'm pointing to this slide because there's this post that I made called How Do Robot Manipulators Move? And at the very bottom, there are a couple of resources. Where are they? I should have probably planned this better. Here it is. So yeah, there's a couple of books and courses that are very nice, in my opinion, the best. So I would take a look at Modern Robotics by Kevin Lynch and Frank Park off of Northwestern University. There's a new book coming up from Chris Hauser called Robotics Systems, which has some really nice tools. There's also the course and accompanying free online textbooks by Russ Tedrake on robotic manipulation. I think these three are probably where I would start as the top three resources, and the other two are a bit more specific, I would say.
Thanks for sharing. Alessio, do you want to go ahead with your question?
Yeah, okay, thanks. Thank you for the very interesting talk. And I was wondering, since you spent most of your career in planning and system design, basically, nowadays there is an interesting raising interest into VLM and VLA for planning. So I was wondering, what is your opinion toward those methods, and if you think they could be really useful, since you are in Ray Institute and you were in Boston Dynamics and all these institute.
Yes, this is the talk that I mentioned for Monster Number 1 talks a little bit more about this, so I will just put up the slide and then answer your question. Where is it? Yeah, this one right here. I think someone linked it in the chat too. But yeah, no, you're right. I think one of the issues with the kind of system design solution is that you need to create this whole task planning system and abstraction for each specific problem that you solve, right? So even if you have a beautiful task planning for home service, if you need to then change something for like industrial assembly, then you have to go like reinvent the whole planning domain and predicates and skills, and that sucks. So yeah, VLAs and VLMs have been very good at making these systems generalizable, both in terms of, you know, you can tell a VLA to run any basic skill and it will do it, like pick up this random object and put it here. But you can also ask a VLM for the truth value of predicates, right? You can say, hey, do you think I've completed inserting the part on the tray or something? So I think a lot of research has come out with using these tools, but I think today I would argue that you're not getting the same reliability from those tools as you do from a very purpose-built point system. So there's a big research opportunity there to kind of combine all these, what I consider mostly the interpretable qualities that you have from engineering system with the kind of state-of-the-art performance and generality of the learned systems. I think there's a lot of really nice work that still needs to be done there, and I'm looking forward to what the next few years bring.
Thank you very much.
Mm-hmm.
Thank you. Any other questions? I can ask one while folks are probably thinking of stuff as well. So I have two questions. Maybe I'll get started with one. So in this current day and age of vibe coding, a lot of the tools that people are kind of bringing together, how do you see folks being able to contribute positively to open source without getting exhausted from random PRs being kind of posted of, you know, super inflated code in some cases?
Yeah, so the thing with vibe coding in general is that it still pays off to have experience. Like, lots of experienced software engineers that I talk to that are using these agents, they're basically taking a high level direction approach, right? So they might start by prompting a tool to, hey, design me an algorithm for motion planning. And then you'll get something and you might say, oh, this code is kind of complicated. Why don't you like extract this out and put it here? So you actually have like concrete suggestions in the same way that you would be reviewing like an entry level engineer's code, right? I think the pitfall happens when you don't really have that background or that muscle of like knowing the decisions that will make your generated code useful. Is that you say, oh, well, it seems to work, so I don't have to do anything else here. Like it gives me the answer that I want, and that's all I need. And then you're basically like, having the agent create a ton of technical debt for yourself. So I would say like lots of people that I speak to are using these tools and basically telling them to refactor things in the way that they want them to go. And I would certainly go that way. I don't know if that answers your question. There's more about the contributing to open source.
Yeah, I think that's helpful. I had a question also about how folks can start off contributing positively. Like, I'm sure that you started somewhere, to get into the open source community and start sending PRs and solving issues. So if someone's interested, someone on call decides, okay, I want to kind of get started with this, what are places that they can kind of look at, or what suggestions would you have for them?
Yeah, so there's two ways of doing it, right? And they're both kind of listed here. The first one is to kind of start your own projects and help to grow them. So these were a lot of these projects that I made. I created, something really basic that just, showed how to do something. And then as this code became promoted, then people started catching word of it and then finding issues that needed to be fixed. Or I've even talked to people that have, said, hey, this simulator is really cool, but I need this particular feature, like multi-agent simulation or something. So, can I work towards adding it as part of my thesis or something? So you could basically look for these kind of entry-level tools, and kind of improving them for your own work. Actually, there's one person on the call here, Sanjeev, who I met, quote unquote, by him picking a random issue that I had on one of my repos. And I think now he's implemented maybe 2 or 3 different features in this PyRoboSim tool. And they were increasing in complexity. So that's definitely a good strategy. And shout out Sanjeev for that. The other approach is to engage with some more official programs, right? One that I want to point out here is the Google Summer of Code. This is one that I worked on through Move It, and I think I will actually start a Summer of Code this next year for RoboPlan, where Google actually sponsors open source contributions, and they will actually pay the contributor a little bit of money to actually like contribute to an open source project for one of these existing tools. So definitely look out for projects like these. Go to existing open source repos and look at the issues list. Offer help in working on some issues. I think usually the maintainers, if they're good, they will provide you with some pointers on what to try and will help you review. So these are a couple of ideas.
That's helpful. Thank you. We're very close to time, so I just wanted to point out a couple of questions in the chat. So there's one from Scott asking about automatic test generation. So if you have any thoughts on methods for synthesizing tests given the hardware or software to be tested, we'd love to hear it.
Yep. Yeah, I'll answer that and then I'll go to the next one. So yeah, I think there are absolutely other test generation methods that are important. So fuzzing is really good for things that you talked about, particularly when you're dealing with things like Python, where you could pass in a bunch of arbitrary data types to your system. You could really like mess up your system. I think other things that are very important are regression tests, particularly for the algorithmic side of robotics. So a regression test is where you basically say, hey, when I wrote this test, when I ran this algorithm, this is exactly the output that I received. And maybe I even, I got the output in this amount of time. And then as you're making more changes, you validate that you're still getting the same output so that you haven't regressed in performance, both in terms of the output that you get and maybe in how fast you get it. So yeah, I think the entire gamut of different types of testing is very important for robotics as you get more and more professional in quality. Guess I'll answer Yassine's question really quick too. For any recommended technique for synchronizing observations and images for policy inference, there actually isn't that much, and it's actually a really good opportunity for the community to produce something. I think there are a couple of tools, for example, in the ROS ecosystem that will look at the timestamps of messages that came in and try to do like interpolation or synchronization to get yourself, the one golden observation for policy learning. But I don't think there's any standard solution beyond that. I think everyone that's doing policy learning professionally is building their own homegrown stack for doing this synchronization. So if anyone comes out with a good open source tool dedicated to keeping around these buffers and doing the interpolation for policy learning, you're going to have a really popular tool on your hands. Yeah. And please let me know when you make it, because I might want to see it.
Perfect. I think that positively kind of wraps up the talk for today. Thank you again, Sebastian, for joining us and presenting all of the lessons that you've learned in the years that you've spent contributing to open source and the tools that we all get to use today. And thanks everyone else for joining us. This is the last talk for the year with Talking Robotics. We hope to be back again in January with another speaker for you folks to hear from. Thanks for your time.
Thank you all.